Welcome back. We are discussing about the Laplace inversion of special function e exponential of minus a root s, where a is positive. What we have done so far is you have seen that this Laplace inversion, as you see, this is your I is I denoted as that you have seen that it is actually root 2 by pi times Fourier sine transform of this function. That is this is if you write like this, you can write this is equivalently, because I changed a to xi. So, what you have is L inversion of e power minus, instead of a I write xi root s of as a function of t. So, this is what you have. So, for this you need to calculate this Fourier sine transform of x into e power minus x square by t x square t, and to do that, so what you have is this is related with Fourier sine transform of x into Fourier sine transform is related with actually Fourier transform of x into e power minus x square t. So, you calculate Fourier transform, so that what you have is e power minus xi root s, xi positive will be this one. So, this is where we are now. This is exactly where we are. So, we calculate this Fourier sine transform of basically Fourier sine transform, I use this Fourier transform of x into e power minus x square. So, ultimately what you see is the Laplace inversion of this function is now this integral you have to evaluate, which is simply Laplace Fourier transform of that function. So, this is exactly what we have. So, to evaluate this we can use direct technique, just put it as e power minus something square. So, that is the idea. With that idea you end up this is your Fourier transform. So, once you have this Fourier transform of to do this, to get this Fourier transform, what we consider, actually we consider without x, you look at the Fourier transform of this, that we find that this is what we get, and this is exactly what you have. And now you differentiate with respect to xi both sides to see that to see finally that Fourier transform of this x into e power minus x square t, you end up getting this one. So, here I made a small mistake. So, 2 root 2 I missed, I put it, I removed root 2 because I root 2. So, what we should have is 1 by 2 root 2 t. So, it should be 2 root 2 e, and this side minus I xi, bring it to this side. So, that is become minus I by xi. Okay. So, 2 root 2 as it is and root t. So, this is exactly what you have. So, you should have 2 root 2 here. So, that is exactly your Fourier transform of this. Now, this gives me immediately, once we know this, you know from this Fourier transform of Laplace transform of Laplace inversion will be I times root 2 by times whatever we have got. So, let me write that. So, this implies a Laplace inversion of e power minus xi root s as a function of t is simply I times exactly what you have is I times root 2 by pi times this integral, I times root 2 by pi times this Fourier transform, that is exactly what you have is minus I by 2 xi root pi by 2 t e power minus xi square by 4 t. So, this is exactly what you have. So, if you simplify this, minus I and I will become plus 1, and root 2 goes here, and what you have is 1 by root pi, and you have pi xi comes out, and then root pi goes, root pi by 2 and root 2 pi by goes. So, you get 1. So, you have 2 xi root t. So, you end up getting xi by t. So, you have 2 t. So, you have 2 t. So, I missed t outside. So, from here, so you have a 2 t is actually 2 t comes out. So, there is a t here. So, that comes out. So, you have 1 by t, and that is exactly your Fourier transform. So, if you use it here, 2 xi t. So, you have this times t. Okay. So, you have root t, and the t is here and xi is here and 2, and root 2 by this one and this one will go, and you have I minus I is 1. So, you have this into e power minus I square by 4t. This is for t positive. So, if you write it, rewrite it 1 by, what I do is I put it as t times. So, t you can write it as square root of t square here. So, when you differentiate this integral, what you have is minus I x, there is no xi here. So, there is 1, and this side you have this. So, you finally end up this, you bring it minus I. So, you have xi only in the top. So, you have xi here from this, xi by 2t. So, you have a xi comes up actually. So, that is what exactly your Fourier transform. Now, if you use this here, so instead of in the down, so you have in the numerator, instead of in the denominator, you have in the numerator. So, you have xi divided by this. So, you end up getting xi by square root of this is 4 and this is t cube 4 and then where is the pi? So, some pi is also missing here, root 2 by root pi by t. Well, there is no pi here, again there is again mistake here. So, you see when you differentiate, this side as this and right hand side is this. So, from this you can write this, there is no pi here. Okay. So, there is no pi here, 2t xi by 2t and root 2t is here, and that is xi by root t and e power minus I square by. So, this is what you have to use. So, minus I xi by 2t and pi is not here. So, you have only 1 over this. So, if you use this instead of, so I have this one times. So, what I have is instead of pi I have 1 by 2t I xi by 2t into this one. So, this is exactly what you have. So, now if you do this, I minus I that is 1, and you have root 2 goes, and you have 2 comes down, and you also have root pi is here, and root t I can write it as t square. So, finally, you end up getting 4 pi t cube e power minus I square by 4t, t is positive. So, this is exactly your Laplace inversion of e power minus xi root s of t. So, if I replace xi by a, so let me write. So, finally, you end up getting, so therefore, so you have Laplace inversion of e power minus a root s, that is where we started, as a function of t. This will be, instead of xi you put a by square root of 4 pi t cube times e power minus a square by 4t. So, this is exactly your Laplace inversion of the function you want. So, not only that you need this, you can get this from you can also get this from the Laplace transform table, inverse transform of e power minus a root s. From this you can get you can also derive 2 more related functions. For example, if you look for Laplace transform of Laplace inversion of e power minus a root s over s. Okay, if you want this, that is L inverse of e power minus a root s by s as a function of t. So, what is this one? This is actually equal to e power minus a root s by s as a function of t, which is equal to, you know that this is you can write like L inverse of L of 1 is 1 by s times L of this function, L of e power minus a s is L of this function. So, you can write this L of a over 4 pi t cube under root e power minus a square by 4t. So, this function, if you calculate the Laplace transform, that is e power minus a root s from this. So, if you write like this, and this will be equal to L inverse of L of this together is Laplace transform of this convolution function of this and this, that is a by square root of 4 pi tau cube and e power minus a square by 4 tau into this I use as a f of tau, and this is a g is 1. So, g of t minus tau, that is simply 1 itself. So, you have d tau. So, this is exactly what you have. So, if you Laplace inverse and Laplacian will go, so you have simply this is the one. So, this is equal to this. So, Laplace inversion of this function is this. So, this you can simplify by writing by making use of this change of variables a square by 4 tau, you take it as x square. So, you have a by 2 root t equal to, let us say, x. Then a times minus 1 by 2. So, first write a by 2 times t power minus half, derivative is minus half times t power minus 3 by 2 equal to into dt equal to dx. So, this you can use this. So, let us say tau, this is t is not t, so this is tau. So, d tau. So, if you use this, what you get is 0 is if you put 0, this is going to be infinity, and you put tau equal to 0, x is infinity, and you put this one, this is going to be a divided by 2 root t. That is, so d tau is dx by 4 dx by a times tau power 3 by 2 dx. That is what you have. Okay. And this, if you use a by 4, that is 2, that is root 4 times 4 pi times tau power 3 by 2. So, this gets cancelled, this gets cancelled. Okay. So, you end up getting, and you have a minus sign, that is a minus, dx is d tau is minus of that. So, I put the minus here. So, you can rewrite this as 2 root a by 2 root t to infinity, because of minus I can interchange these limits. So, you have 4 times. So, what happens to this? This is going to be you get this is 2 root 2, root 4 is 2, 2 goes. So, you have 2 by root pi comes out, and then and you have e power minus x square for this function, okay, because of this. So, you have e power minus x square dx. So, this is exactly what you have as a Laplace inversion of this one. Okay. So, Laplace inversion is simply this function. Okay. So, Laplace inversion of e power minus a root s by s, a function of t, is equal to 2 by root pi times a by 2 root t goes to infinity e power minus x square dx. So, this is one. You can get again from this, you can also make use another Laplace inversion, that is Laplace inversion of, you can also get Laplace inversion of, you simply differentiate this quantity, differentiate since a is positive, a is between 0 to infinity. So, a is positive. So, you can differentiate both sides with respect to a to get, what you get is Laplace inversion, that is an integral whatever the integral. So, if you integrate, so you end up getting in the integrand you have this one, if you differentiate with respect to a, it is going to be minus root s comes out as an integrand. So, that is the only difference. So, you have minus Laplace inversion of root s e power minus a root s by s. So, this gets cancelled and become here. So, this is what you have on the left hand side once you differentiate with respect to a, and so that you have here 2 by root pi, and this one if you differentiate with respect to a, and it is going to be minus sine, and you have 1 by 2 root t times wherever x is there you just put e power minus a square by 4 t. Okay. So, this is what you have. So, if you simplify this 2 goes, minus minus goes, and you have 1 by root pi t e power minus a square by 4 t. This as your Laplace inversion of e power minus a root s by root s. This is what you get as transform. So, you have a is positive. So, the same thing here. So, a is positive. So, you have now derived the Laplace inversion of 3 special functions. These are the 2, and you have one more here. So, this is where you have done originally all the work. A is positive again here. So, this is how you can get this Laplace inversion. Now, we make use of these 3 special Laplace inversions to look into the boundary value, initial boundary value problem for the heat equation. So, let us look into some other problem. Let us solve this problem of heat equation in a semi-infinite domain. So, let us consider a semi-infinite rod, that is you have a semi-infinite rod which you have a rod which is at 0 to infinity, this is at 0 and this goes to infinity. Up to infinity you have this rod, and the temperature in this rod initially u at x 0, you keep it temperature 0. Initially the rod is at 0 temperature, and you have u at 0. At this end I try to give the temperature, I feed for all times as f of t, some general function I can give. At infinity I expect this heat to go to 0 as x goes to infinity. So, these are the boundary conditions for the heat equation, because this models this temperature in a rod is modeled by the heat equation. So, if I write mathematically a problem of heat conduction in a semi-infinite rod, let us say. Okay. So, the problem is initial boundary value problem is to find solution of this is to solve ut equal to some k times uxx, x is a bit positive and t is also positive, x is from 0 to infinity, t is time 0 to infinity, and you write these boundary initial conditions. So, initial condition is u at x 0 is 0, and boundary conditions are because two boundaries 0 and infinity. So, you have u at 0 t as f of t, and u at u x t goes to 0 as x goes to infinity. So, this is the second boundary condition. So, if you to get the solution out of this, as usual we apply Laplace transform for the t variable, application of Laplace transform. Application of Laplace transform to the equation with respect to t gives, what it gives is you are doing with respect to t. So, this becomes s times u bar of x s minus u at x 0. So, u at x 0 is 0. So, that goes, that is the left hand side, is equal to k times u x x is dou square by dou x square of u bar, that is simply u bar of x s. So, this is for x positive. T variable is gone to s variable, that is actually complex variable. So, that is what it is. This is the equation it has become. So, this implies dou square u bar by dou x square minus s by k times u bar equal to 0. This is for x positive. So, this is your equation, and now if you apply the boundary condition, initial condition I already applied. So, if you use the boundary conditions gives u bar at 0 s. After applying Laplace transform for this condition, this becomes f bar of s, and u bar of x s goes to 0 as x goes to infinity. So, these are the two boundary conditions, and we solve this ordinary differential equation. So, if you solve this, so what is the solution of this problem? U bar of x s, this is m square, this is a complementary function is m square minus s by k is 0. So, that makes it m equal to plus or minus square root of s by k. So, you have c1 times e power root s by k, that is a constant, times x, and plus c2 times e power minus square root of s by k times x. This is your general solution of this equation. Now, you apply these two boundary conditions to get rid of this c1 and c2. So, as x1 xs goes to 0 as x goes to infinity, c1 has to be 0, because otherwise if c1 is non-zero, this cannot be this cannot go to 0. Okay, because of this condition c1 has to be 0. Okay, since u bar of xs goes to 0 as x goes to infinity, c1 must be 0. So, this is gone. So, you have u bar of xs is c2 times e power minus root s by k times x. So, what is now we apply the first condition, that is this. If you apply this, and you get u bar of 0 s, which is equal to f bar of s. This, if you put x equal to 0 here from this equation, c2 times e power, when you put x equal to 0, this is simply 1. So, you have c2 is simply f bar of s. So, that implies u bar of x s. The solution becomes f bar of s times e power minus square root of s by k times x, and this is for x positive. Now, you invert this, inversion gives u of x t. So, what is the inversion of this? This we already know. So, this is like f bar, see, this is Laplace transform of this into Laplace transform of something, some function for this. So, that is a convolution between 0 to t. This is f of let us write t minus tau here. So, that this function let us put tau. So, what is that one? You already have seen just now Laplace inversion of this function. A is this a by square root of 4 pi t cube. Okay, a by square root of 4 pi t cube. What is a here? Square root of x by k, that is your a by square root of 4 pi tau cube. I have to write in as a tau here, and then e power minus tau square, or rather what is exactly you have a by square root of 4 pi t cube times exponential minus a square by 4t minus a square. A square is x by k 4t 4kt, that means, okay, t is tau. So, I put tau. For this you so I had the convolution for this function and this function. So, you have this is a final form. So, this is your solution of this differential, that initial boundary value problem, whatever you have. As this is for t positive and x positive. So, this is your solution for the boundary value problem. So, that we have. Okay. So, this because you give the f, so you can simplify this integral again by rewriting this as e power minus this I think a square, right. So, you have x square. So, x square becomes a square is a is this. So, you have x by k, fine. So, this is how you can solve this. By the way, just a minute. So, x is not within the root, x by this is actually x by a is x by root k, sorry x by root k. So, you have x square, this becomes x square by k. So, you have this is the form you get. Okay. So, this is x is outside this root. So, you have x by root k is your a is, so a divided by a is x by root k divided by square root of 4 pi tau cube times e power minus a square, that is x square by k 4 t, that is 4 tau. So, this is the form you should get. Okay. So, you could solve this boundary value problem, initial boundary value problem for a temperature of a rod, semi infinite rod which is at rest, and you keep pumping the heat here for all times. So, eventually as you see at infinity it's you always expect this to be 0 temperature. As t goes to infinity, what you end up is finally t goes to infinity, what you expect is if f is constant, if you keep pumping some constant temperature, eventually as t goes to infinity uxt becomes a constant all along the temperature, right, all along the rod you will you can expect this. So, as a remark you can write as a remark. So, if f of t is constant, let us say t naught, some fixed temperature you keep pumping at the end of the rod at x equal to 0, what you expect is for all times your temperature is integral 0 to t, x comes out, x by root k comes out. So, you have root k is 4 pi k, and you have integral 0 to t times e power minus x square by 4 k t 4 k tau by t root t tau root tau cube. I am writing tau root tau as d tau. So, again you write this as you consider x by 2 root k tau as a new variable, let us say some x1, then this implies dx, sorry you need let us use a new variable x1, yeah, okay. So, x by 2 root k, there is a constant, and tau power minus half, that gives me minus 1 by 2 times tau power minus 3 by 2, which is into d tau is equal to dx1. So, what you have is 1 by tau root tau d tau is equal to 4 root k by x with minus sign with dx1. So, that is what you have to write. So, this becomes x by square root of 4 k pi 4 root k pi times integral. Now, when you put tau equal to 0, so it is going to be infinity here, and you put here, so it is going to be x by 2 root k t, and you have this minus sign for dx, you have 4 root k by x times dx1, and you have this will become e power minus x1 square. So, this is how it is this integral. So, x is a constant, this goes 4k goes 4k will not go. So, root k will go, and you have this goes finally make it 2. So, you have minus, you can interchange the limits, that is x by 2 root kt to infinity, you have 2 comes out, e power minus x square, rather you can put it as some tau square d tau, as x1 is a dummy variable, you can put it like this. So, what you expect is as t goes to infinity, as x goes to infinity, as for all times, okay, this is what is your u of x t. So, as x goes to infinity, as t goes to infinity, eventually what happens, as t goes to infinity, you end up getting u of x t as so I did not write this f of t. In the place of f of t you have to write t naught. So you have t naught which has a constant all the times 2 t naught. So you have a 2 t naught times integral, as t goes to infinity this becomes 0 to infinity e power minus tau square d tau. This is actually root pi by there is a root pi which I missed, so divide by root pi. So root pi is not cancelled. So you have by root pi this one. So this quantity is root pi by 2. So this root pi by 2 and 2 by root pi cancel. So you end up getting T0. So that is expected, as you see in this rod, infinite rod. If you keep pumping constant temperature here, so let us say if we say T naught, constant temperature, if we keep on doing it, eventually as t goes to infinity you pick up any point at any point x, eventually as t goes to infinity at bigger times it will reach that same temperature will reach this point. That is what it means. Okay. As you see, as t goes to infinity, this temperature at every point x it become T naught. Okay. So that is what it is. So x is positive. So this is how you solve this initial boundary value problem. Let us look into some things next very similar to this problem, that is if you change the boundary condition at x equal to 0, instead of pumping the temperature here, instead of pumping the heat at this end 0, you can just insulate it, for example, or you allow the flux, okay, you allow the heat to go inside, okay, that is you give the rate of flow of heat, okay, not a constant rate. So at this point you allow some heat is passing from this end to this end. So that is a flux, that is a heat flux you allow. So the rate of that is called rate of flow of heat you prescribe. So at 0, that means dou u by dou x at x equal to 0 and t for all times, that is 0 t, you give it as some function of t. Instead of u, you give the temperature, what you give is dou u by dou x you provide, that is the rate of change of heat, the rate of heat flow. The rate of heat flow you allow this heat to pass from this, from outside to this or inside. Inside is anyway 0 temperature. So if you allow as a minus, so that is going to be you are allowing this to go inside. Okay. So let us give like this minus gt, just think of g of t depending on the sign of g. So you see that is either going outside or inside. Okay. So that is how your condition here, all other things are same. So how do I write this as a mathematical problem? Solve ut equal to k times uxx, x positive, t positive, and this initial condition is as it is. So you have u at x t equal to 0 is 0, initially temperature is 0, and boundary conditions, only boundary condition is this, that is dou u by dou x at 0 t is equal to g of t, t positive, and u of x t goes to 0 as x goes to infinity. So this is another boundary condition. Okay, these are the boundary conditions. So you solve, how do we solve this? Everything else is same except the equation when you apply the Laplace transform, you get the same thing. Laplace transform gives the ODE that I write directly as dou square u bar by dou x square minus s by k u bar equal to 0 for x positive, and your boundary condition is dou u bar. So this is with respect to t you are doing. So you get dou u bar of 0 s by dou x equal to g bar of s for x at x equal to 0. Okay. And this is one boundary condition. Other boundary condition is u bar of x s goes to 0 as x goes to infinity. So again the solution for this becomes the C1 has to, because of this C1 has to be 0. C1 is the coefficient of exponential of root s by k x. Okay. And what you end up is C2 times e power minus square root of s by k times x for x positive, and you have by applying this you lose the other solution, that is C1 times e power plus root x by k times x. Because of this, that C1 has to be 0, so C2 is this. You apply this boundary condition now, dou u bar by dou x at x equal to 0 s is actually equal to C2 times, you differentiate this and put x equal to 0. So if you differentiate with respect to x, you have minus root s by k times e power that one. So that becomes simply 1. So you have this. So this is equal to g bar of s. So this makes it, that gives me what is my C2? C2 equal to minus root k by s times g bar of s. This you substitute into the general solution. So you get u bar of xs as minus root k times g bar of s times e power minus root x by root s, x by root k times root s divided by root s. Okay. So this is what you have for x positive. So now you get the inversion. So inversion will give you, now you are going to use Laplace inversion of e power minus a root s by root s. This is as a function of t, if you recall, this is actually is e power minus a square by 4t by root pi t. So this is what you have to use. So you get inversion gives, now inversion gives u of x t as minus root k is common, as a constant comes out. For this, Laplace transform of g and Laplace transform of this. So this Laplace transform of this is Laplace transform of this function is this one. So you write that. So you have there is a convolution of g, Laplace transform of g, for which you have a g bar of s. Laplace transform of g of t is g bar of s. Laplace transform of this function is this function. So with a, of course a is x by root k. X is positive, root k, k is a constant, that is also positive. So you have this convolution is 0 to t times g of t minus tau, and this one I will put it this function I will put it as a t. So a is 1 by root pi times tau times e power minus a is a square is x by root k is a, so a square is x square by k 4t 4kt you can write. This is exactly your 4k tau d tau. So this is the convolution you have to apply. So this is equal to minus root k by pi integral 0 to t g of t minus tau times 1 over tau root tau times e power minus x square by 4k tau d tau. So this is your solution for this problem. Of course x positive, this is x positive and t positive. So again the same way you can if you give constant temperature, constant flux, you allow the heat. There is a difference between heat and temperature. Earlier problem you are providing the temperature, you are keeping that end with the constant temperature. Here you are allow the heat to go inside from outside to inside the rod at x equal to 0, or you allow the heat from the rod to go out. So that means you allow the heat to go out. Okay. So that is what is the second problem. So for which this is the solution. So if you use a constant g as a constant, you can see that if you just take if as a remark, you can get this if g of t as a constant. So this flux is a constant rate. If you take it as a constant, what happens is that u of x t simply become minus root k by pi times t naught times integral 0 to t, and you have e power minus x square by 4k tau divided by root tau d tau. So, again you can use make use of this x by 2 root k tau as a new variable x1. So, you get x by root 2 k, and you have minus half times tau power minus 3 by 2 d tau equal to dx1. So, if you use that, minus root k by pi times t naught, this is going to be at 0, it is going to be infinity, this is going to be t, which is x by 2 root k t, and you have this becomes e power minus x1 square, d tau by root 2, d tau by root tau is dx. So, what happens, dx by 4 dx 1 by root k, of course root k comes out by x, and then this is going to be of course you have a tau. So, tau is up. Okay. So, what is tau? Tau is from this you can see, you can get this tau as x square by 4 k tau as x1 square. So, you have a tau is x square by x1 square 4 k. So, tau you can write x square by x1 square 4 k. So, xx goes. So, you end up finally getting of course, there is a minus here. So, the minus sign makes it plus, and now if you k by pi t naught, this you make it, this you change the limit. So, you have x by 2 root k t to infinity, and you have 4 goes here, k root k. So, this k goes here, this k and this root k goes here, and you have x here, x comes out, t naught x, and then that is all. So, you have x, this is x, if you use x1 you use as a dummy variable, you have a tau power minus 2 times e power minus tau square d tau. So, this is your x u of x comma t. So, this is exactly what you have, that is all right. So, you have x square is this, yeah. So, this is your solution, what you get as for x positive, t positive. So, again as x goes to infinity, you can think of, if you keep pumping the constant flux, you allow them into the system, eventually you see that at any point x, as eventually as t goes to infinity, you end up getting some kind of, as t goes to infinity is going to be 0 to infinity, this integral you have to get this integral, and as whatever be the, that is your temperature, okay, temperature in the rod. So, we look at some other relevant problem. We look at the relevant initial boundary value problem for a infinite rod from minus infinity to infinity, where you end up similar getting e power one of these Laplace inversions. We will just write that problem. So, let us look at the relevant problem that if you solve an infinite rod, that is ut equal to k times utt uxx, that is x is now full infinite rod, that you have a 0 minus infinity to infinity. If I have infinite rod, x belongs to full R and t positive. Suppose you have this, and initially you have a temperature of this infinite rod is having, you provide some f of x as your initial condition. There is no boundary. So, what you do is at infinity it has to be bounded, you cannot allow it to be 0. Okay. So, just to give a 0, physically at infinity there is nothing like infinity. So, at infinity you can expect the temperature to be 0. So, u of x t goes to 0 as mod x goes to infinity. So, both the cases, both the infinities it has to go to 0. So, let us use this to, these are, you have two boundary conditions here, okay, this involves, and you have, this is the initial condition. So, what is the solution if you follow the same technique? You end up getting Laplace transform gives ut, that is s dou u bar by dou sorry, this is u bar of xs su sxs minus u at x0, that is minus fx, that is the initial condition I used, that is the left hand side, k you have u bar of xs for which you take two derivatives with respect to x. So you get dou square u bar by dou x square s by k minus s by k times u bar equal to you are dividing with k, so that you have minus fx by k. Okay. So this is x belongs to minus infinity infinity, and if you apply these boundary conditions, what you get is u bar of xs goes to 0 as x goes to infinity, and also u bar of xs goes to 0 as x goes to minus infinity. So these are the two conditions you have to use and to solve this ordinary differential equation. So we will solve this, and you end up getting finally, again you can end up using this Laplace inversion of this, you end up using Laplace inversion. You will see that you need to find this Laplace, you need a Laplace inversion of e power minus a root s by root s, same similar type of Laplace inversion you need, that I think we will see in the next video, and along with other boundary value problems where you can use, you can get other type of, other than these special Laplace inversions, you may get other type of Laplace inversion you may need. Okay. So we will look at some more examples of initial boundary value problems for heat equation, so that you can utilize your Laplace transform and get your solutions. Okay. So if you cannot use the Laplace transform, maybe other methods may work. The advantage of this Laplace transform is when other for certain problems in some domains, when you are solving the heat equation or the wave equation, you may not be able to solve by other methods, maybe, or maybe because of the difficulty with the other methods. If you use the Laplace transform technique, it is much simpler way you can find the solutions. If you are not able to find a solution by the Laplace transform, that does not mean that you cannot solve by other methods. So other methods may be easier. Where other methods fail, for example separation of variables technique in the differential equations, or some other Fourier transform technique, if it fails, you may sometimes Laplace transform procedure may be simpler to derive the solution. So we will see these other examples for heat equation, and we will look at the other applications of solving integral equations, and you can also solve, you can evaluate certain integrals involving a parameter. These applications we will see in the next video. Thank you very much.